I'm currently in the process of moving my CPU build from breadboards to PCBs on a proper backplane. In the previous episodes, we've built this port display PCB which shows us the data going into and coming out of the register file on a bunch of LEDs, and this flags and move and immediate buffer PCB, which stores the flags of the CPU and contains the move and immediate buffer that allows us to move data between registers and load immediate values from the instruction into the register file. Today I want to take these two PCBs, plus all of the register PCBs that we've already built, and move them onto a proper backplane. And this backplane will also have to include the address decoders that select the individual registers, which we had on the side next to the registers on the breadboard thus far. So let's get started by first drawing up a schematic for the backplane. Let's start with the port LEDs. Let me create a new footprint and let me copy over all the interesting bits from the PCB. So these are the interesting pieces of the PCB layout copied over into a footprint. And interestingly, it also copies over the 3D models for the pin header and all the pads and all the Silkscreen. So this is pretty convenient. The only thing we have to do is go in and renumber all the pins, because copying these over from the layout will just keep the original pin order. Let me save this footprint. And then let's create a schematic symbol for it. I'm going to use the symbol wizard for this, probably just to a single inline package such that the pins are just lined up on one side. And now let's associate this symbol with the footprint we just created. And both the symbol on the left and the footprint on the right have 37 pins in total, and they seem to line up properly. Alright, let me save the symbol and let's add it to the backplane. And there we go. Let me hook up power and ground to get started. And then let's wire up the buses. Let's see how this looks on the PCB. That's pretty cool. That's the footprint we've just created, and that's basically the layout of the port display PCB. And the cool thing is that we can spend a little bit of time on the footprint to add the proper Silkscreen labels, and then whenever we place this on the backplane, we already get the properly labeled Silkscreen. And we get the 3D model for free because we just copied over the pin headers into the footprint. Let's create a footprint and symbol for the register PCB next. And again, let me go through and number all the pins properly. And then let's create a symbol for this. And then let's go add this to the backplane. So that's one register, and we need 7 in total. So let me copy paste this a few times. So these are the 7 registers. Let me update the PCB layout. And then last but not least, we want to create a footprint and symbol for the flags and move and immediate buffer PCB. Alright, let me again go through the pads and number them properly. And let me also create a symbol. And then let me add this to the backplane as well. Alright, let's also add it to the layout. Okay, so that's the main PCBs placed on the backplane. Let's now go in and add some of the other bits and pieces that we need. One of the things we'll have to add to this backplane are the address decoders for the registers. We used to have those on a breadboard to the left of the register file. So let me add those chips to the schematic. We'll use the top address decoder to pick one of the registers for writing. And similarly to what we did on the breadboard, we're going to skip output number 0 because register address 0 we've put aside to indicate that no register is selected. Then we'll use the second decoder for read data port 1. And then the third address decoder we'll use for read data port 2. And on the breadboards, we've connected the same select signals that select read data port 2, also to read data port 3, but offset by one register. And I think we'll want to do the same thing here on the backplane. Now these address decoders also have 3 enable inputs. 2 of them are active low and 1 of them is active high. On the breadboards we've been using these to, for example, disable read data port 2 when we're driving an immediate onto read data port 2 and to disable writing back to the register file in certain conditions. So we'll definitely want to have write and read enable signals brought out to a pin header on the side that we can connect to. But read data port 2 needs some additional consideration. On the breadboard, if we enable immediate mode, we're disabling the read data port 2 of the register file itself, such that no register drives onto this port, and we can drive the immediate value onto that bus instead. And so in case we enable the immediate buffer, we want to disable this address decoder here such that none of the registers are driving something onto RD2. So let's use the same signal on the flags and move PCB. And correspondingly, we also want to consider the read enable 2 for the immediate buffer, such that when read enable 2 is inactive, when it is high, we want to have the GPR backplane let go of the read data port 2 entirely, so nothing should drive. And this already works here for the address decoder. If read enable 2 is inactive, is high, the address decoder is disabled and none of the registers will drive onto RD2. But we also want to add this to the flags and move PCB over here, such that the immediate buffer is also disabled if read enable 2 is disabled. And then while we're up here, I think we also want to have just one single move output enable signal, and it should probably be active low because that's what we used on the breadboard. And I think that should be it in terms of enabling and disabling these address decoders. Let me tie off the remaining enable signals in their enabled state. Another thing I think we'll want to have on the backplane is pull down resistors for the write and read data ports. Because we're working with CMOS chips, we'll want to make sure that if no value is driven onto these data buses, that they flow to a defined value. They get pulled up to VDD or pulled down to ground. And finally, another thing to consider is the number of PCBs that need a clock signal. We have the registers up here, 7 in total, which require a clock, and we also have this flags and move PCB, which requires a clock. So in total, we have 8 loads on the clock signal here. And as we build out the CPU, we're only going to be adding more and more chips that need a clock. So part of building out these larger systems is coming up with a clock distribution scheme with a clock tree. Instead of wiring the clock signal up to everything in the system that requires a clock signal, you would use a tree of buffer gates to distribute the clock signal. And to make sure that the clock arrives at all the components in the system at the same time, you would just have to make sure that there's the same number of buffers between every component in the system and the root of the clock tree where you're actually feeding in the clock. As a rule of thumb on modern silicon, if you're building actual chips, you would use a fan out of 4 rule to build these buffer trees and also the clock trees. So every buffer in the tree, you would hook up to at most 4 other chips, such that every buffer only has to drive 4 other chips. But on PCBs with the 74HC series, you can usually get away with a fan out of 8. If you have a buffer, it can probably drive up to 8 other chips pretty reliably. There's the 74HC34 chip, which is a pretty simple buffer, and they also come in the single gate variant, which is pretty handy for this kind of distribution scheme. And all we have to do is make sure that all the other parts of the system, all the flip-flops and whatever needs a clock, has one of these buffers somewhere in between its clock and the root clock to make sure that the delays are balanced across the system. The only thing left to add are a bunch of headers on the left and right, and maybe at the bottom, where we have all the signals of the backplane available and where we can plug in the other parts of the system. I'm pretty sure there's actually a mistake here. I think this isn't a move mode, but this is an immediate mode, because we're picking whether we want to have a 4-bit sign extended immediate or an 8-bit immediate. And then on top of these connection headers with the actual signals, we were also planning to have a whole bunch of power, clock, and reset headers. That looks almost complete already. Let's do a electrical rule check. Okay, no warnings or errors. So that means each net has at least 2 pins, which doesn't mean too much, but at least there's no obvious issues and mistakes. Let me quickly update the layout to have all these new components there. All right, things are getting busy. Let me go roughly position these headers. Pretty neat. These headers on the side are going to make it very easy to connect this up to the other parts of the system and to fresh new breadboards that we're going to build in the future. Let me go and place the remaining components and then route the signals for this PCB. Alright, that's most of the signals routed. We still have this clock buffer here that we need to place somewhere. Let me find a spot for that and then wire it up. At the bottom of the backplane here, I think it would be nice if we had a few additional pin headers for the write data port and the 3 read data port, and maybe the flags write and read data, such that we have a convenient location where we can plug in additional connections from the breadboards we're going to build out in the future. Last but not least, let me add a power LED and a few decoupling capacitors close to the chips. And I think we also want a USB-C port just for us to plug in power. This is a USB-C socket, and with USB-C, in order to draw adequate power from the V-bus from the 5V supply rail, you have to connect two 5.1 kilo ohm resistors between the CC1 and the CC2 lines to ground. And one thing I would like to do is I would like to have another copy of this clock buffer on the backplane and have that output be available on a header. Because what is likely going to happen is that we're going to build up additional breadboards on the side, and those breadboards need a clock, and that clock needs to come from the same level of the clock tree. And so if we have a buffer available on the backplane that isn't used for anything on the backplane, that will provide the clock for the rest of the system. Let me distribute the capacitors, the clock buffer, and the handful of new connectors across the backplane. Now with all these long vertical and horizontal signals running all across the PCB, it's going to be difficult to distribute power properly with just a copper pour. On some of the other PCBs, I've used a VDD and a ground copper fill on the top and bottom layer to distribute power, which works well if you have sufficiently interrupted signals. But here with these long-running signals crossing the entire PCB, these copper fills are going to be cut apart and it's going to be difficult to distribute power that way. Let me switch this to a 4-layer PCB, which is going to be a little bit more expensive, but it's pretty important on the backplane that we have a very solid power distribution. And by adding 2 layers into the PCB that carry exclusively the power rails, we'll get a very good power distribution. So we'll have a ground plane and a VCC plane on the inner layers. Let me go and drop a few vias for the power connections. So that's the power planes and the power rails all hooked up. As a final step, let me go and clean up the Silkscreen a bit. Alright, this looks pretty good. This is going to be a pretty exciting backplane, and it's going to give us a pretty good power connection for all the components that we put there, and a good clock and signal distribution. Let me order the PCB, and then once I get it back in the mail, let's go and assemble it. I got this back from the manufacturer, together with a pretty large stencil. So to get started, let me apply some solder paste to one of the PCBs. That looks pretty decent. Next up, let me populate this PCB with the components. I'm gonna go from smallest to largest, so let's maybe start with the capacitors. Next up, we have a few resistors, one for the power LED, and another two for the USB port. Then we also have a blue power LED. Then we have a bunch of pull-down resistors for the data ports. And we also have two small single-gate buffer chips. And last but not least, the 138 demultiplexers. And then as the final piece, let me add the USB-C port. Okay, that's all the components populated. Let me fire up the hot air gun and then solder this up. Now that everything is soldered up, let me give the board a quick cleanup off camera and see if all the solder joints are correct, and then we'll come back to mount all the pin headers. I'm gonna start out with the small 2x2 pin headers that we have here for power and ground. Next up, let me add the other 2-row pin headers. Now let me get the single row headers on the side out of the way. And since these headers are all on the same grid and I want them to be properly soldered on that grid, let me use a pin header to keep them straight. Then let me add the power and clock headers at the top. And then let me do the same thing for the pin headers at the bottom of the backplane. Okay, that looks pretty good. Let me deal with the headers for the flags move and immediate PCB. Then let me deal with the control headers of the registers that run vertically. And then last but not least, we have a whole bunch of pin headers that carry the data signals into and out of the registers. I think I've got all the components on there. Let me give this a quick cleanup and check off camera again, and then we'll plug it in, power it up, and see if it does anything. Let's see if we can power this up. We now have a convenient USB-C port at the top that we can use for this. That looks pretty good. The power LED goes on, and no apparent smoke from the chips we have. Let's start simple and add the port LED PCB at the top. Let's see if the port connections work. Pretty nice. So we have the data ports available here on the side, and they're properly connected to the data ports running vertically here. Next, let me add the PCB that contains the flags register and the move and immediate buffer. Let me also add a power rail here on the right hand side. Let me set the clock to 0. And then let's see if I can clear out the flags register. First, let me set the flags write data port to 0. And then let me activate the flags write enable, which makes the flags write enable LED go on. And now when I toggle the clock, you can see the flags register get cleared to 0. And when I change the pattern and toggle the clock, you can see the new pattern appear here in the flags register. Alright, so the flags still seem to work. Let me go steal a few register PCBs from the CPU build. Let's see if we can read from the registers. So we can read from this register, and we can see its outputs appear on the read data port. And we can also read from the other register. Let's try read data port 2, which should also enable read data port 3, but shifted by 1. So this works just like it used to. That's pretty cool. Let's see if we can drive an immediate onto read data port 2 instead. Cool, that also works. And you can see the immediate I've connected here to the immediate port appear here at the read data port 2. And by toggling the immediate output enable line, I can go back and forth between the immediate and the register data. Let me change the immediate mode to 4 bits. That seems to work. The immediate mode is now 4 bits, and only the lower 4 bits of the immediate appear on the RD2 port. And if I toggle the 3rd bit of the immediate, you should see it be properly sign extended and fill up the entire upper 4 bits of the read data port. Pretty nice, that works like a charm. Let me go back to 8-bit immediate mode. Now let's see if we can drive this value onto the write data port. To do this, let me activate the move output enable, which turns the move output enable LED on down here, and you can see that the data appears at the write data port. Let's see if we can store this into one of the registers. And when I activate the write enable of the corresponding register turns on. And when I now toggle the clock, the data gets stored into this register. And then let's try to copy the value in the upper register into the lower register. And if I toggle the clock, this gets stored properly into the second register, which is still selected for writing. This is pretty exciting. It looks like the backplane is working properly. And the port LED PCB and the flags move and immediate buffer PCB we've built in the previous episodes also seem to work properly with the registers we've had for quite a while. So now I think the only thing left to do is to get the CPU back out and integrate this backplane into it. So this is the current state of the CPU with the 2 stolen registers missing. And now that we have this backplane, we can get rid of quite a few things on the breadboards. To get started, let me remove the remaining register PCBs. And then let me get rid of the old backplane and some of the wires that lead to it. And then let me squeeze in the new backplane. And now let's hook up all the data connections that we've just lost by ripping out the old backplane. The ALU needs access to the right data port, which we have available up here. Then we have a bunch of port connections at the bottom of the stack. Then we have the register addresses, which lead to the address decoder. This is now integrated in the backplane, so let me move that over. First, the write address. And we were using the same address also for read port 1. So let me cross-connect the two. And then let me connect read address 2. Next, let me move over the write enable. And the read enable for port 2. The backplane also has an enable for read port 1, so let me tie that to ground to constantly enable it. And for the first test, let me disable the new immediate and move buffer. We'll just keep using the ones on the breadboard for a second. And then let me connect the power of the new backplane to the power network of the breadboards. And let me connect the clock and the reset of the backplane. Alright, everything powers up and nothing catches fire. Let me step it out of reset. And then the first few instructions in the program are going to clear out the register file. Then we're loading the bit pattern 1001 into the first register. And we're flag swapping it, so we're storing it into the flags register. That looks like it's working. Let me step through a few instructions to see if the other registers work. That looks pretty good. There was quite a bit of activity on all the registers. Now, this is still the conditional move test program that we were running the last time we were working on the ALU and the CPU. And at the end of this program, we computed the largest Fibonacci number. So let me hit run and let's see if the largest Fibonacci number appears in the top 2 registers. That looks pretty good. This is indeed 46,368, the largest Fibonacci number that fits into 16 bits. So at this point, I'm moderately convinced that the new register stack works and we can run the existing program. As a next step, let's try to get rid of the move buffer on the breadboard and instead use the move buffer we have on the PCB. To do that, let me permanently disable the move buffer on the breadboard and bring the control signal that used to enable it up to the new backplane. Let's check if this works. And now the new move buffer is enabled and it's driving the 0 immediate on the RD2 bus onto the right data bus. And now after this first load immediate, we're doing a bunch of moves. And so the move buffer is still enabled, but we're no longer in immediate mode. And it's driving the data coming out of RD2 onto the right data port. Pretty sweet, that seems to be working. Now let's do the same thing for the immediate buffer. I'm going to permanently disable the immediate buffer on the breadboard. and instead connect the bit in the instruction that indicates whether we have an immediate to the backplane's immediate enable signal. And since the backplane is now doing the switching between immediates and register data, we can permanently enable its read data port. And to make this work, we also need to take the immediate bits from the instruction and connect them to the backplane. Let's see if this works. The first instruction is a load immediate, and indeed you can see that on the backplane the immediate buffer is enabled, but you can't see anything because we're loading a 0 into the register. So let me skip over the first few instructions. And now we're doing another load immediate, but this time it's a bit pattern 1001, and the immediate mode is enabled again. And indeed, you can see that the immediate appears here on the read data port too. And since we're doing a load immediate, the move buffer is also enabled and copies this value onto the write data bus. And at the same time, the old immediate buffer here is permanently disabled and it's not doing anything anymore. Let me check that this still computes the Fibonacci sequence properly. Very nice, that still works like a charm. So this new backplane has just made quite a few things on the breadboards obsolete. I think it's time to rip them out and make the whole build a little bit more compact and clean. Let me first get rid of the breadboards around the register file. Next, let me get rid of the move buffer. And then let me also get rid of the immediate buffer. Okay, pretty nice. That has cleaned up the breadboards down here quite a bit. We still have a pretty big wiring mess over here though. Let me try to fix that. Okay, that got rid of quite a bit of annoying wiring. Let me also move the clock generator out of the way a bit. I don't want to constantly reach over the build just to toggle the clock. I'd rather have it somewhere much more convenient. Let me add a power rail in the middle just to make certain connections a bit easier. And then let's see if this still works. First, we're clearing out the register file. Then we swap a value into the flags and play around with it. Then we're testing a bunch of comparisons. Alright, that still works. And let me hit run, and we should compute the largest 16-bit Fibonacci number again. Pretty nice, that still works. This is still the number 46,368. So that's using the new move buffer and the new immediate buffer. And the only thing left to do is to actually make use of the flags register here in the register stack. Now instead of the flags coming from this register on the breadboard, we want the flags here coming from the flags read data port of the register stack. And the new flags presented to the flags register will connect over to the flags write data port. Let me also connect the flags write enable to the backplane. And then finally, let me remove the register chip. So now this flags write enable LED up here is no longer working. We have to look at the PCB down here, but the other flags related LEDs should still be up and running. Let's see if this new flags register works. First, we're loading 1001 into a register, and then we're using flag swap to write this new value into the flags register. And as you can see, the flags write enable turns on down here, and when I hit the clock, this new value gets stored in the flags register. Then we're doing a bunch of conditional moves, which works. We basically get the value for the carry and the 0 flag, and then the carry and the 0 flag inverted. And then we do the same for the sign flag and the overflow flag. And again, we get the sign and the overflow flag and the sign and the overflow flag inverted. So that seems to be working. And then let's compute our Fibonacci number again. And yeah, this still is 46,368. Very nice. So it looks like this new backplane for the register file, plus the new breadboards we have that also contain the move buffer and the immediate buffer, plus the flags register, they all work. On top of that, we were able to get rid of the move and the immediate buffers here on the breadboards, which has cleaned up this part of the CPU quite a bit. And also we have a bunch of new wiring terminals available here such that we can keep the wires a bit outside of the build. And then as we build out these backplanes and we connect the backplanes with these side connections here, a lot of these connections here will go away, and eventually we'll only have wires to the breadboards where we're building out new functionality of the CPU. And one thing I noticed is that the clock generator breadboard I have here is quite a bit flaky in terms of the power supply and its power rails. So it might be worthwhile turning this into a small little PCB. Now, one thing I'd like to point out is that we had a little bit of a hold time violation with the flags register when it was on the breadboard. If you look at the flags register now, you can see that the carry flag is set and all the other flags are cleared, which is what you would expect because we've been doing additions until the carry flag was set, at which point we broke out of a loop, cleared all the registers, and then halted the processor. But when we were using the old flags register up here, if you've paid close attention in the previous episode and the beginning of this episode, you would actually see the flags end up in some weird intermittent state, not always displaying the correct value. And I think what has been going on there is that the move and load immediate instructions would sometimes corrupt the flags register. And I think this is down to a hold time violation. Basically, the register requires the data at its inputs to be stable for a very short period of time after the clock catch, just so that it has enough time to latch the data in and store it. But when we read instructions out of the program memory, we're using the clock directly as an input to the flash as an address, and we're also using the clock directly to connect to this latch. And even though this flash has a long propagation delay, it takes 70 nanoseconds to produce a value, it's very likely that as soon as an address changes, the output that it displays becomes corrupted almost immediately. And these registers often require the inputs to be stable for a few nanoseconds after the clock catch. So the instruction data changing so quickly after the clock catch might have been just close enough to trip the breadboard register into a hold condition violation. We're going to look at setup and hold constraints in much more detail in a later episode when we try to determine how fast the CPU can actually run. But now that everything is on PCBs and we have a proper clock buffer and clock tree on the backplane, the clock signal is likely clean and fast enough to push the register out of this hold time violation again. So at some point in the future, we'll look into this in a lot more detail and actually try to figure out if there are other places in the CPU where we have this danger of a hold time violation occurring. For now, I think this looks really exciting. In the next few episodes, I think I want to do the exact same thing for the ALU and also for the program memory. The program memory breadboard has been pretty stable, it's just producing 16 values out of a flash ROM, so I think that's something we can definitely put on a PCB. And then at a later point, when we get fancier with the program memory, we can go back and create a new PCB for that, but I think that will serve us well for quite a while. And the ALU is a pretty massive stack of breadboards with wires going everywhere, and having this on a much more compact PCB is going to make the build a lot cleaner. And then when we have the ALU and the program memory on their own PCBs, we can put them on the backplane we've already laid out together with the program counter. And that will give us a small little group of PCBs that will act as the core of the CPU, and then we can start building off of that. We're in desperate need for some instruction decoding such that we can get back some of the immediate instructions that we used to have. We'll also want to have some memory and a load store unit to read from that memory and write to that memory, and then look more into the control side of the CPU. We need to figure out how we can stall the pipeline if some functional unit like the ALU or the load store unit isn't able to make progress because there might be a memory contention, or what to do when there's no new instruction ready for the CPU to execute, maybe also because of a memory contention. And then based on that, I think we'll be able to add the first few out-of-order execution features. Somewhere along the way, I'll also add the traditional LCD screen to the build such that we have something to print output to, which makes it easier to see if a program does the right thing, especially once we start to build more complicated programs. And the out-of-order execution will be particularly useful once we have functional units that take multiple cycles to complete, such as a multiplier or a divider. But until that point, I think we have a lot more PCB work ahead of us. And we can compute Fibonacci numbers, which is also something. Thanks a lot for watching, like and subscribe if you want to see more of this, and see you next time.